Manifest is an exciting new vision for math education. It's an instructional framework for executing that vision, as well as a growing set of resources that bring the vision to life. What is Manifest? Let's find out. We'll start with this. If you're like me and can't read Mandarin Chinese, this probably looks like a wall of meaningless symbols. I want you to pay attention to just how little feeling you get from it. There's no content there. It literally feels like nothing. In a second, I'm going to put something different on the screen, and I want you to pay attention to the flood of meaning that you get when I do. So one last time, think about how empty you feel looking at the Chinese symbols. And now, did you feel that rush of meaning? The images, smells, and physical sensations that filled your head and body? Why did that happen? If you could read Mandarin Chinese, it would have happened in the reverse way. The truth is, there's no inherent meaning in either of the language's symbols. The only meaning we draw from the world comes from concrete, visceral experiences. So the only reason this phrase caused you to experience something was because you spent a lot of time in your early schooling years forcefully linking these arbitrary symbols to the visceral experiences they represented. So now when you see this phrase, you feel a soaking wet dog. And the reason you didn't feel anything with the Mandarin Chinese was because you never spent time forcefully linking those symbols to the concrete experiences they represent. Enter math. One of the most common complaints made by learners is that math doesn't mean anything, especially after elementary school. That's because when they see math symbols, they don't instantly perceive visceral, concrete experiences. They might be able to manipulate the symbols in legal ways, like this, or maybe even like this, and we count that as understanding. But notice that it doesn't even come close to crossing over the bridge into meaning. What about graphs, you might ask? But graphs are usually no different. We are tricked into thinking they contain meaning because they are visual, but that's an illusion. They are still a very abstract representation of the information. Here's an analogy with the dog to help you understand what I mean. Imagine if we, instead of linking the written English word dog to real dogs, we instead link the word dog to a dog's position in a taxonomy tree. It is certainly visual, but it's not a dog. That's what graphs are. Manifest aims to solve this problem by engaging learners in activity that directly links mathematical symbols to the concrete visceral experiences that they represent. As we'll see, this means envisioning quantities as concrete units such as temperature, length, luminous intensity, time, rotations, and number of objects. To keep things systematic, Manifest uses the 7 scientific base units as a starting point. These include mass, temperature, time, length, luminous intensity, electric current, and amount of chemical substance. To round things out, we also consider the act of counting the number of objects or actions, as well as rotations. Using Manifest simulations, learners can then explore quantities and expressions in terms of these quantities. Take the length simulation, for instance. Type any number and a line segment takes on that length. Negative numbers as well as expressions work just as well. But 30 inches is a different experience than 30 rotational degrees. To explore numbers expressed as rotations, learners use the rotation simulation. For a completely different experience, students can feel 30 degrees Fahrenheit. Or 30 discrete objects with the number of objects simulator. One beautiful thing about Manifest is the way it extends the visceral experiences into advanced mathematics, where it is often sorely missing. By thinking of one quantity as an input and the other quantity as the output, functions are naturally formed. This square here, for instance, represents a function that takes a number of objects as an input and outputs a length. Where in life might the number of objects or actions affect length? Here are 3 examples from one of the instructional videos from the Linear Functions microcourse. In life, there's an infinite number of situations where the number of objects or actions in a situation affects the length of something. Here's an example. Imagine you took a penny and stacked another penny on top, and stacked another penny on top, and stacked another penny on top, etc. The number of pennies, the number, affects the height of the penny stack. So a number of objects is affecting the length of something. Here's another example. Imagine you had a string that has a certain length, and then imagine you had a pair of scissors and you're going to cut that string. If you cut it once, now the length of the string has gotten shorter. So one cut affected the length of the string. Now imagine you cut that again. Now you have 2 cuts and the length of the string has changed again. So again, a number of objects or a number of actions is affecting the length of something. Last one. Let's say you've got a goldfish of some sort. Now each day you've got to feed that goldfish a certain number of pellets. Well, let's say you decide to feed that goldfish 3 pellets every day. You do that every day until it grows up, and maybe it grows up to be this long. But maybe if you had given him 4 pellets, he would have grown to be even longer. Again, a number of objects or a number of actions has an effect on the length of something. And here's a video showing how our simulation for number of objects affecting length expresses these types of relationships. The length versus number of objects simulation allows you to control 2 different quantities. On the left side, it allows you to control a certain number of objects, each represented as a dot, which can be negative. On the right-hand side, separately, it allows you to control the length of something by setting it directly. This can be rotated in different directions. The number of objects is given the name x, and the length of the segment is given the name f of x. And currently the values are separate. Changing the number of objects doesn't affect the length over here. The simulation allows us to make a connection between the 2 quantities by simply entering the name of the number of objects in the definition of the length. So for instance, by putting x as the length, we can now change the number of objects and the length corresponds. We can put any function or expression with x inside and we'll get a similar connection. Now this says that the length is equal to the number of objects plus 2. So the number of objects is 4 and the corresponding length is 6. And if we change the number of objects to 5, the length increases 1 as well to 7. So in this way, the length versus number of objects allows us to explore different connections between the number of objects and the length of something. With 9 possible inputs and 9 possible outputs, there are 81 different visceral experiences that can be represented using these units alone. We can add a 3rd dimension to this image if we realize that any one of these input-output pairs can be related to each other using any type of function we could think of. We could use quadratic functions, cubic, trigonometric, exponential. The list goes on. We've seen a situation where number of objects affects length in a linear way. How about rotations over time using a trigonometric function? Easy. Just open the simulation, type in the function, and press play. How about length affecting luminous intensity using a cubic function? There's a simulation for that. Manifest helps learners explore this rich space with lessons that force learners to make direct connections between symbolic mathematics and the visceral world. To use Manifest's resources or to learn more, visit manifest.education.